Morning. Yeah, so if you want to take pictures of your exams, because we're about to go through them, or not exams, sorry, your homework. So we're about to go through them, and then I guess just turn them in here, make a stack, and then we're going to go through the homework, talk about it, and kind of answer any questions about the exam coming up on Thursday. Hear you guys chattering about DJ leaving.
Yes.
So I'll be taking one of his classes, the other 3110 for the civil students. So it'll be 3 lectures a day, Tuesday, Thursday, starting next week for me. So if I'm a little bit, well, for you guys, my voice hopefully will still be here, unless I lost it the previous day, Tuesday, right? But it's going to be rough for me. I expect I might have to shortcut on some course logistics, not in any way that will harm you guys, but I might have to account for participation in more of a general sweeps, because I just haven't got that organized as much as I should have, and it's not looking likely that I'm going to have more time to work on that. So it's going to be interesting. Okay. Anyhow, how are you guys doing? How are you feeling about the exam? Here you're covering water softening in the VJ's class for those of you who are in it.
Yeah.
Cool. That's handy. I had no idea, so but that's hopefully a good reinforcement there. All right. Any questions or concerns for the exam or about the homework before we get going? Finally blessing people after first sneezes. For 2 years it's been like, curse you, don't give me COVID, right? No. Okay. Anyhow, so homework 3, let's start talking about it. So problem 1, we were going to compare the difference between a plug flow and a CSTR reactor for use in disinfection. Essentially, reactor is going to be designed to achieve a 3-log reduction in cryptosporidium using ozone. Has a coefficient of specific lethality given there, 1.78 liters per milligram per minute. And we're going to assume that the dilution coefficient is 1, meaning it's an ideal reactor with perfect mixing where it's supposed to have mixing. If the flow rate of the process is 0.1 cubic meters per second and the ozone is applied at 0.42 milligrams per liter, we have to answer the following questions. So the target is a 3-log reduction, but we're not necessarily there to start with, is kind of the implication here. We're designing it that way, and we're going to test 2 different cases, the CSTR and the plug flow reactor, to see how close we get. So part A asks, how much crypto will a CSTR with a 100 cubic meter volume remove? And so essentially what we're looking for is removal. So the removal percent is going to be proportional to the amount that's remaining, except it's going to be 1 minus remaining, right? If we're talking about fractions. So the removal is going to be 1 minus the n over n naught, because n over n naught is what we've got at the end of the process compared to what we had at the start, right? That's the fraction remaining in the system. So 1 minus that should be our removal. And we could give the final answer as a percent if we wanted to. That would just be multiplying that by 100%. So kind of starting from the end of the question, that's what we're going to be looking for. Now to get there, it's going to be a disinfection system. So we're expecting first order kinetics. We've got our concentration C, 0.42 milligrams per liter. We've got K, which was 1.78, and that was liters per milligram per minute. And we have Q 0.1 cubic meters per second. This reactor is going to simply be equivalent to this, CSTR N naught, an N, and a flow rate going through. Okay, there's also going to be our concentration there of our disinfectant. So we have all those parameters, and the question is, how is this affecting N and N naught? We could go ahead and calculate the theta. It's V over Q. So right now I'm just sort of putting all the different knowns and unknowns together here, organizing so that we can kind of put everything in place. So this is going to be 100 cubic meters divided by 0.1 cubic meters per second. 0.1. That's essentially multiplying by 10, so that's 1,000 seconds. The seconds will come on top. Okay, so that's pretty much all the pieces. Now we need a mass balance. So we're going to do a mass balance on N, and we're looking at, assuming steady state, the reactor is going to be operating for some time. It'll be Q, N coming in, so N naught, minus N leaving. So it's minus Q, N here, plus our reaction term, which is going to be a negative V K C F. Now we have the N and the C there because our K here is given as the coefficient of specific lethality. We need to multiply, if we wanted to, we could say K times C, that's K star. We talked about. Okay. However, that's how we got it, and so here we essentially just need to simplify, solve for N over N naught, and then take 1 minus that. So I'm going to go ahead and put the N terms on the left. We'll have Q N. So we've added that over. We'll add the other part over, plus V K C N equals Q N naught. I'm going to divide everything by Q. So we'll have N. I'm going to go ahead and factor out the N's on this side too while I'm at it. So 1 plus VKC. But I'm dividing everything by Q. So this will be theta. And then we end up with N equals N naught over 1 plus theta Kc. That will change to N over N naught equals 1 over 1 plus theta Kc. So we've seen this before in different systems, first order decay in a CSTR. We can put in our numbers, and that becomes 1 minus 0.243. I'm going to post this. This will be posted, and the recordings are going to be up as well. And that's going to give us a removal of 0.757, or 75.7%. Okay. So hopefully that was relatively straightforward. Do you have the added complication of having the K and the C, putting those in there? And by the way, the K, and I don't think I wrote this out, but the K here this is in milligrams per minute. So what we ought to do to convert this before inserting it here is convert it to seconds. So we could say times 1 minute per 60 seconds. And that should get us in terms that we need to solve the problem. So we can say, if we take 1.78, divide that by 60, that should give us the K value that we ought to be using there. So K is 0.0297, so 0.03 essentially. 0.03 liters per milligram per second. Once we do that conversion. That way our seconds line up when we have a theta here. It's 1,000 seconds times that value, 0.03 liters per milligrams per second, multiplied by our 0.42 milligrams per liter for the concentration. Okay, does that make sense? Maybe.
Yeah, it's
Okay. It's all good.
I'm comparing it to the like mass balance that we did like at the way beginning, and so I'm just following.
Yeah. Okay. And one thing that can confuse that is the C here and the N. The C is going to be constant because we're assuming that the ozone stays constant throughout this process, and so that's why it might be worthwhile just to substitute in a K star that accounts for both of those, and carry that through, and then it feels just normal like any other thing we've ever done. So you can do that, and you ought to know you ought to remember this relationship here when it comes to disinfection, because that's going to be important. You're going to have to do that sometimes, or go between them. Okay. Part B asks how much crypto will a plug flow reactor with the same volume remove. So essentially it's the same problem, 1 minus n over n naught. And if we want, we can take that into percentage. That's what we're looking for. And now the mass balance here, we're going to treat it like a batch reactor that goes through the system for some amount of time, right? So theta is remaining unchanged. That's 1,000 seconds. And our mass balance is as if we had a batch reactor. It's going to be V dN dt equals V K C N, and we integrate, and we end up with n over n naught equals e to the minus k c, and instead of t, we're going to do theta, right? So that's the one difference there, is we've got a known time frame there with the theta instead of just some time that we're counting on our watch in a little batch reactor. Okay, so with that, we put in the numbers that we had a moment ago, and we say, so n over n naught, that's going to be 0.044. We put in those numbers, and 1 minus 0.044 then is 95.6%. I don't mind if you leave it as a fraction or percentage. Either one's fine. Okay. That makes sense? Let's see. All right. Part C then asks, what is the minimum volume for a plug flow reactor that is required to remove 3 logs of cryptosporidium? So essentially we're solving for V this time when we know that n over n naught has to achieve a 3 log removal. That means the amount remaining has to be 0.001. If you wanted to, you could start with the fact that 1 minus n over n naught should be 0.999. It's another way to look at 3 log removal. But could also just say, well, if you remove 3 logs, that means there's 1,000 times less, so the amount remaining in the first place is 0.001. Okay, so then all we need to do is take that same mass balance and rework it in reverse to solve for the volume, given everything else is known. So we can take 0.001 equals e to the minus k c theta. And here, take the natural log of both sides. That'll be natural log of 0.001 equals negative kc times, and instead of theta, I'm going to put it as v over q. Solve for v, and we should get q times the natural log of 0.001. This is going to transfer the negative over that divided by essentially k star here, k times c, and that'll be our solution. And when we put in the numbers, then we should get a volume of 55.4 cubic meters. And something is not adding up here in my mind. So 100 cubic meters a moment ago only removed 95%, and now we're having something smaller. So I think I put in, I think what probably happened is in this one I put in the wrong K. Probably did not put in the proper K for
that. This number for this one, but for like the last one, I got like 99.999, and the one before that, I got like 92. Yeah, I got 92.6.
So you got 92.6 on this one. You got, oops, sorry, I just went all the way. Yeah, I think what happened was I was running through it too quickly in Excel, and I didn't do this part probably. So let me pull that up. I have this problem solved in Excel. It shouldn't take but a moment. Yeah, I think no, okay. Can you guys confirm if part A is correct if we put in that 0.03?
I think your screen might be
Yeah. I'm just asking. Can you confirm that if you put in this 0.03, you're getting this number for me? I am looking at Excel on my other screen.
I had like 0.02974 times the 0.42 number to do like the K star thing essentially, but I didn't really mark it as K star. I have 1 over 1 plus 1,000 seconds times 0.2974 times 0.42.
What was your final answer if you put in this number?
If you put
0.
in that number, 0.07.
Yeah.
Okay, so this is not adding up then, correct?
Yeah.
Okay, so
So
then
if you put in that kind of 0.03 times 0.42.
so we're just going to back up for a moment and make sure we do this right. And so the process here ought to be correct. I don't think once we converted there, I don't think I missed anything. Okay, yeah, I didn't realize that in my Excel I had a different volume. That's what it was. I'm glad to see that that was the issue. Okay, so for K star, you guys, I think were just saying you had 0.747 or 748, I guess. This would be 1 over seconds, or no, that's 1 over minutes. Sorry.
Would that be 0.03 times 0.42?
I can't do that in my mind. Hang on.
with that K value that you have, the 0.03, if you plug that into the formula that you have, I got the same answer as you. If that makes sense.
Okay.
So like
Hang on.
using that K and that concentration, I got that.
Okay, so one moment though, because in my Excel sheet I had volume as 25 cubic meters for some reason, and so that messes up the theta. That was where my mistake was coming in, I believe. So now I'm getting, and I do apologize for the confusion. Now this is coming out to be 0.0743, which I think is what you guys said. Right, good. Okay, which would be 1 minus that. Is going to give us essentially 92.6%. Okay, so only one of you were confused when I went over this in the first place. The rest of you had the right answer and just pretended like everything was fine, right? And you guys have to double check me. I'm allowed to be wrong too, okay? You don't always have to be the wrong ones. Okay, so with this would definitely be the wrong spot as well. Okay, so and honestly, if I had changed the volume for 25 instead of 100, the numbers do come out like I was showing them, which are a little bit better of a comparison in a way. Anyhow, so the this number then, like you said, is a very small number, 3.87 times 10 to the minus 6. Really, it's 3.88, if I rounded properly. And so 1 minus that is going to be pretty small, or very close to 1. And it's so close to 1 that I'm just going to call it 1. You could take this decimal out 3 places and it's still accurate, even though if you took it out far enough, that would be 99999, whatever, right? Something like that. So I'm going to call it 100% removal, approximately. You understand it's not really 100%. But there you have it. Okay, so that's kind of the correct version. So feeling a little better about it? I'm sorry. Okay. I try to change my questions each time a little bit, and I did change that one, and I did account for that change, but I had forgotten that the Excel had a different change that I'd made on another occasion, and yeah, that was not so good. Okay, however, this last problem should still remain the same. and the same answer, right? And now it makes better sense that you don't need a full 100 cubic meters. Yeah.
For A and B, I just assumed it was first order and just plugged into the first order equations and got the same answers. On the test, should I just do the mass balance and not assume instead?
Okay, so the question for those online is somebody recognized it was first order, just went straight to the derivation, the derived mass balances for first order systems, and you got the answers because that's the technically correct approach. And should you not assume that and just derive it? I would say if it's clearly just simply a first order problem in a known reactor type, that's fine. If you're confident enough to recognize exactly the setup and everything, go for it. I would encourage you to be ready to derive it in case there was some difference in the system. There are plenty of problems that say something like this. This chemical is injected into the system at a rate of, and then it gives you mass per time. And if you're stuck in the bubble of thinking about it each Q, like a mass per time, for example, Q times C gives us mass per time, right? If you take a look at the units, that ends up as mass per time. But if a problem gave you just some value in milligrams per minute, how do you insert that into your mass balance here? It would go into like right here, for example, or something. But if you're not prepared for that, that's probably going to throw you off, right? So I would encourage you to be prepared to do this. If you just memorized it and did a pretty good job recognizing it, maybe that's a B instead of an A if there's a problem like that. It can probably get you a pretty good way through these types of problems, but it'll benefit you to really master it by being ready for the derivations. It's a good question. Okay, problem 2, we have a chlorine problem. Chlorine used as a disinfectant. Essentially, we're adding sodium hypochlorite, NaOCl. It's going to completely dissociate. So the first reaction is completely going to Na plus and OCl minus. From there, the chlorine side of it, the OCl, is going to be in equilibrium. And it's going to reach that pretty quick. And we've got an equilibrium constant for that. We have a disinfection reactor that's treating a flow of 2,500 liters per minute of water. The pH for this water is 9.6. And so the first question is, what will the ratio of HOCl to OCl minus be? And so essentially what we're looking for is HOCl to OCl minus. Another way to write that would be to say simply HOCl divided by OCl minus. And I'm using brackets here because we are talking about on a molecule comparison. Turns out the mass is not going to be too different because just adding that H, that's HOCl, the molecular weight is something like 60-ish or 61. OCl minus, that would be just 60, so 1 minus that. So it actually wouldn't be too different on a mass or molecular basis, but it does make sense to give it as a ratio for the amount of molecules there. Okay, at any rate, that's what we're looking for. What we have is some information about the pH and the Ka. So we know our equilibrium reaction can be written this way. And right there from the get-go, we can kind of see we have something we can use to convert into this ratio, right? If we kind of invert the system, then we have HOCl on top and OCl minus on the bottom, and we can just separate and get reaction, or get our the desired equation. So let's do that. I'm going to bring it over here. Let's say HOCl, multiplying both sides by HOCl, and divide both sides by OCl minus. So that's going to be equal to, and then we're left with H plus over here, and we need to divide the Ka. So we've got H plus divided by Ka. So that's just rearranging our equilibrium equation. And that's going to give us the ratio that we were targeting, right? So that's going to be simply 10 to the negative 9.6 divided by 10 to the negative 7.54, I think, right? Yeah. Okay, and if we solve that, I mean, first, if we just look at it, right, if you have 10 to the something divided by 10 to the something, you can actually subtract one from the others. That should be something like 10 to the minus 2. So that should be somewhere around 0.01. And if you do then put it in a calculator, 0.0087, pretty close to 0.01. Okay, so that's then the ratio that we were looking for. In a percentage term, 0.87% of the solution is in the HOCl. Which is not so good a thing if you're trying to disinfect water. You kind of want it to be in HOCl, not in OCl minus. So part B says, if the operators decide that a concentration of 2.5 milligrams per liter of HOCl must be applied to the treatment process, how much mass of NaOCl should they add per second if the pH is kept at or lower than 7.3? Okay, so we changed the pH. We're trying to figure out how much mass of NaOCl to add per second to achieve the HOCl concentration to be kept at 2.5 milligrams per liter. So that means the total is going to be something more than that because it's partitioning into HOCl and OCl minus. All right, so the way we can approach this one, well, first of all, add a couple things up here. We need the molecular weight for NaOCl, molecular weight for HOCl. Just getting those set up and in place. So HOCl, that's 52.45 grams per mole. NaOCl is 74.45 grams per mole. Then another thing we can do is we can solve for the molar concentration of HOCl that's required. That's going to be that 2.5 milligrams per liter times 1 gram per 1,000 milligrams, and also times 1 mole per 52.45 grams. So essentially just converting using the molecular weight here and getting that in a form where we can do the molar comparison. Because if we find the moles per liter of this, then we can find the total moles per liter of chlorine as a whole, and then find the moles per liter that we had to add of the NaOCl, and then convert that back to mass and account for the flow rate for the system. So if we do this, our HOCl concentration comes out to be 4.77 times 10 to the minus 5th moles per liter. Okay, so now that we have that, what we want to find is the moles per liter of total chlorine, just going to say, I'm just going to leave it as total. Say for total chlorine, that's going to be the HOCl plus OCl minus. Okay. From here, essentially, what we're going to need to do is find a way to get this into just HOCl terms, because we don't know OCl minus, but we do have HOCl. We could find literally the value here. That works. That works too. I find it's convenient enough to make a substitution here. So given our equilibrium constant, let me go ahead and write it here, Ka, again, coming back to our system of equations, we have OCl minus, all that over HOCl. So we could use this to solve directly for a value here and add it there. That's fine. The way I'm going to do it is simply to rearrange and convert this to put OCl minus in terms of HOCl. So essentially I'm going to divide both sides by the H plus and multiply both sides by the HOCl. So we'll have OCl minus is equal to Ka times HOCl divided by H plus. And then we can substitute that here and put in the numbers. So this will be essentially HOCl, and we could even factor out the HOCl from those two terms. That would be 1 plus Ka over H plus. You don't have to do that factoring out. You can just put it in there in both spots, so there's no problem. I just thought it was nice and simple to do that. That gives us a total value of chlorine. If we put that in, that should be 7.51 times 10 to the minus fifth moles per liter of chlorine total, free chlorine. Okay, so then that's also going to be essentially the amount of moles per liter of NaOCl that we have to add. Now, we don't have an actual concentration of NaOCl, but we did add some amount of it, some number of moles per liter of that. So we can kind of use the brackets even though it doesn't stay that in that form, it kind of works still. So from there we can convert back into a mass unit and say 7.51 times 10 to the minus fifth moles per liter times, and in this case we're going to use the 74.45 grams per mole. That's going to leave us in grams per liter. When we do that, that gives us 0.0056 grams of NaOCl per liter. And then at the end of the day, what we're looking for is mass per second, and that's going to be this concentration we just found times Q. So that'll be 0.0056 grams per liter multiplied by, if we flip back a page, that was 2,500 liters per second. Liters per minute. And so we'll also have to multiply by 1 minute per 60 seconds. Because we wanted mass in grams per second, or some mass unit per second. Okay, and when we do all of that, our final answer should be 0.23 grams per second. Of course, you could do 230 milligrams per second. That'd be fine too. Right, how's that? Any issues? Okay. So problem 3, we have a membrane unit. And essentially, we are looking at a problem that is, I think I may have mentioned in the class, it's kind of describing the sky hydrant type of system where you have a gravity-fed membrane, ultrafiltration, and we're kind of taking a look at practically, you know, if we have a membrane of some typical parameters that you might find for an ultrafiltration membrane, how much water, how much height of water do you have to put on top of the membrane to push it through effectively? And how does that change if you add fouling over time? And I don't know that the amount of fouling is actually realistic. Of course, that's going to depend on the water quality and all of that. So if you have pretty muddy water, maybe that is realistic. So we have a membrane filtration unit for treating water in rural areas lacking major infrastructure. Gravity is used. It's a 0.22 micrometer membrane. The membrane unit houses 22 square meters of membrane area. The membrane system is operated in cross flow under a constant flux regime in order to meet a demand of 500 liters per hour of water. Treated water is 30 degrees Celsius, and make a note that 1 meter of head, hydraulic head, that's a 1 meter water stacked on top of the system, is equivalent to 9.8 kilopascals force. That's very likely directly related to the acceleration due to gravity, by the way. We're talking about kilograms and you know, the density of water being approximately 1 kilogram per liter. Pretty sure all those units are coming into play, and the fact that Pascal uses newtons and all that, that's probably where that 9.8 is coming from. All right. What is the flux across the membrane given the parameters provided is the first question. And I'm asking you to answer in meters per hour to 3 decimal places. Okay, so flux across the membrane, we're talking about J here. J is our flux. And the simplest equation for flux is simply the flow going across it divided by the area that it's going across. And so for problems like this, I would encourage you to, you know, before you jump to the formula sheet and look at all the different formulas that might incorporate a flux J, stop and think about what is, I guess, what is the simplest route and does it make sense, right? So the simplest route would be to say, oh, well, we have a flow rate. We know we're providing that much water, and we were given a membrane area. Yeah, I think we can just use those two, right? So that's our formula for the flux here. That's what we're going to need. Our flow, that was 500 liters per hour, and the area was 22 square meters. So we're going to need to do some conversions here a little bit. We could say that's 0.5 cubic meters, because there's 1,000 liters in a cubic meter per hour, divided by the 22 square meters, and that makes a little bit more sense. And so we can get a flux in meters per hour that way. Do that division. That's going to be 0.023 meters per hour. Okay, so pretty simple for part A. Part B says if the recovery rate of the membrane is 95%, how much water must be fed to the membrane unit to achieve the required permeate flow rate? So that required permeate flow rate, that was the 500 liters per hour, right? Required flow, Q, 500 liters per hour, or 0.5 cubic meters per hour. And if you think about it, by the way, 500 liters every hour, that does seem maybe reasonable for a small community, right? Give plenty of people water to drink. Maybe not giving, 50 homes the ability to shower every day, but you might get 10 homes that ability, or at least providing potable water for cooking and drinking for 50 homes or something. So certainly something that could be beneficial. Okay. Now, essentially what we're looking for is how much water do we have to actually bring to the membrane if we're only getting 95% of that as usable water out, right? So in a simple sense, that you could just take that at a very intuitive level and say, oh, well, we're getting 95% of the water out, so we just take that flow rate, divide it by that 0.95, and that should be the amount total that we need to put into it. And you'll see that exactly what comes out if you actually do, so QP, we would say, if we were to draw, I guess, a diagram here, where we have a feed, a permeate, and a Q rejected, Q permeate, and a Q feed. So our Q permeate, that's this guy. So we can call that our demand. If we take a look at our equation for R, the recovery, that is simply QP divided by Q feed. And so we can solve for Q feed that way, just as you probably could have done simply intuitively had you been thinking like I was just mentioning. So that's going to be that. Let's see, we need liters per hour, so we'll go ahead and leave it in the liters per hour units. That's all there is to it, right? So that becomes 526.3 liters per hour. I'm going to sit down because it's always just a little bit of hunching here. All right. Okay, so any questions or issues there? All right, then. Part C asks, when the membrane is clean, we have some resistance. That's 1.8 times 10 to the 13th per meter. Like I warned you in class, that's a very big seeming number, but again, our membrane is much thinner than a 1 full meter, right? So for whatever it means physically, that's 1 meter is definitely more length than we really need to consider practically. So for whatever help that is. Okay, so how many meters of water? This is talking about, if we have a water tower, let's say a tank up there supported by some structure, how many, what distance of water do we need above the membrane unit to give us enough pressure to give us that yield? Okay, so in this case, we need another flux equation because we still know our flux, right? We calculated our flux. We have that. That hasn't changed. But now we're looking at the pressure required. And so if we take a look, we have a formula. The flux is equal to the transmembrane pressure divided by the total resistance, RT, times mu. So that's going to be the equation we can use. We can get mu because we know our temperature. We just talked about, we were given our total membrane resistance, and we can find that transmembrane pressure, which is going to relate to the height of water we have, right? So that's going to be, if we were just to write it out this way, that's going to be the flux times the resistance times the dynamic viscosity of water. So RT 1.8 times 10 to the 13th per meter. Mu, if we go and look it up, and again, you will have that lookup table. That's going to be 7.98 times 10 to the minus fourth kilograms per meter per second. Have I posted the updated formula sheet for you guys? May not have. Okay, I'll do that. Right after class. That way you'll have that as a reference to study from, to know what you'll have on the exam. Okay, but you had it last time, but these lookup tables, just keep in mind the table itself, in where it describes the units, has the 10 times 10 to the minus third in the unit. So this looked like 0.0798 or 0.798, but the units are times 10 to the minus third kilograms per meter per second. So the dynamic viscosity in the units that we use is going to be a small number. It's going to be times 10 to the negative third or fourth. So just keep that in mind as you're working the problems. Okay, we said from the last problem flux was 0.023 meters per hour. We have seconds in our dynamic viscosity, so we need to convert one or the other. Go ahead and convert the J here to be in seconds. So that'll be 6.31 times 10 to the minus 6 meters per second, essentially dividing by 3,600 seconds per hour. Yeah. Okay, so then we can put all those things into our equation, TMP, and we can double check the units, by the way. It's going to be meters per second times 1 over meters times kilograms per meters times seconds. That's going to leave us with essentially kilograms per meter per second squared, which is the units for pascals. And when we put it in the numbers, we should get essentially 90.7 kilopascals. So I went ahead and converted it to kilopascals. You could leave it as pascals, but then we have that relation that we were given a minute ago, the start of the problem, that said 1 meter is equal to 9.8 kilopascals. So it's going to be handy to have it in kilopascals regardless. So then we can say 90.7 kilopascals times 1 meter per 9.8 kilopascals. That's going to give us our answer of how many meters do we have in our system. Turns out that's 9.25. So just under 10 meters of water stacked on top. That's going to be right around 30 feet or so, right? So that seems like a reasonable height to stack some, to store a storage shed that you can have some decent engineering to keep a lot of weight, a lot of water up high, but certainly something that's feasible. Especially if you have some geography that can make use of maybe a steep hillside or something like that. Okay, so part D says, during the operation, membrane fouls continuously such that 5 times 10 to the 12th meters per meters of resistance is added every 20 minutes. How many meters of water will be required to supply the 500 liters per hour after 1 hour of operation? So if we're adding that much resistance to the membrane every hour, or every 20 minutes, and then we're looking at 1 hour later, essentially we're taking 5 times 10 to the 12th per meter, and we're going to multiply that by 3 because there's 3 sections of 20 minutes in an hour, right? So we could do times 60 minutes over 20 minutes, right? Or whatever. Whatever you want to, however you want to conceptualize it, we've got three sections, right? So we're multiplying that by 3. That's going to be 1.5 times 10 to the 13th per meters of resistance added. And then we'll need to recognize, so this is our fouling, and the R total. In the last problem, or in the earlier part of the problem, we just were given a membrane resistance and that was it. So that was our total. But in truth, the R total is going to be the resistance from the membrane plus the resistance from the fouling plus any other, we don't have any other information, cake layer or whatever. And so really what we're just going to do is take 1.8 times 10 to the 13th plus this 1.5 times 10 to the 13th. And that's going to give us 3.3 times 10 to the 13th per meter. My hand wants to write times 10 to the minus something every time. Every time. Okay. So with that, then we just need to solve that TMP equation again. So we're just plugging in the new resistance. That's going to be J times R total times mu. So if you did this in Excel or a calculator with memory, it's pretty simple to just swap a couple numbers there. And you get, this time, a transmembrane pressure of 166 kilopascals. And then, of course, we can multiply that by meters per kilopascals. And that'll give us 16.96 meters. So about 17 meters if it's fouling that fast. So that presents a problem. If it truly is fouling that bad that fast, chances are we're going to need a new pump, a new storage thing, something. So instead, maybe we stop it and backwash it every 20 minutes or every hour or something like that. Perhaps even set up a system that does that automatically. Or perhaps in reality, they don't foul that bad. And you can do it once a day, and that takes care of business just fine. Which I think that's more likely the realistic scenario for the sky hydrant that I learned about some time ago. All right, any issues, questions with that? Okay, so we'll get on to problem 4. Here we have a sample of water at pH 10.5. It's got 39 milligrams per liter of carbonate and 24.5 milligrams of bicarbonate. And so the question first is, ignoring the contribution of H plus and OH minus to alkalinity, what would be the alkalinity here as CaCO3? So just as a quick reminder, if we take a look at the alkalinity, and in the parentheses here, denoting that it's either milliequivalents per liter or it is as CaCO3, essentially what we're talking about is we've already accounted for the charge differences. So this is going to be equal to the HCO3 minus plus CO3 2 minus. And here's where, if we were talking about molar units, we'd have to do 2 times this, because the way alkalinity is, what we're referring to as alkalinity is the acid neutralization capacity. So how many protons can it neutralize? And something with a 2 minus charge can neutralize 2 protons, right? But if we're using these parentheses, that means we've already converted it into a unit that has accounted for that. If we were not ignoring OH minus, we'd put that here, and then we'd have us subtracting the H plus, but the problem says we're ignoring those, so we're just going to ignore them. However, that's going to be our equation for the next time. This would technically include other species too if there were any others relevant, but we have a pretty simple system here. And so the real challenge or task is to convert the carbonate and bicarbonate into the units as CaCO3. Okay, so molecular weights here for HCO3 and carbonate. Going to be 61 grams per mole and 60 grams per mole. And our equivalent weights are going to be related. We're going to need our equivalent weights to do the problem. Equivalent weight for HCO3 minus, it's essentially 61 because it's dividing by 1. That's going to be milligrams per milliequivalent. And for carbonate, we're dividing by 2 because of that, the 2 charge. So that's going to be 30 milligrams per milliequivalent. And we need that because our equation to convert to as CaCO3 is essentially it's going to be taking milligrams per liter of X times the equivalent weight of CaCO3, which is 50, and divide that by equivalent weight of X. So that's our equation to get to convert from milligrams per liter of something to milligrams per liter as CaCO3. And the equivalent weights there, that's what's accounting for the charges, the difference in charges in case there's an issue there. Okay, so that gives us a way to calculate our HCO3 minus our bicarbonate and our carbonate. Once we've got those, we can find that the bicarbonate, that's 20.08 milligrams per liter as CaCO3. And for our carbonate, that would be 65 milligrams per liter as CaCO3. So the total then, just adding the two together, is 100.9. Yeah. That's a good question. I read from the wrong spot. That is definitely not. That's the answer for the next one. Thank you. Impossibly is how. As would be obvious if I was actually looking at the numbers instead of just copying. That should be 85.08 milligrams per liter as a CaCO3. Okay, so one person awake at this point. One person was awake for problem 1. Let's see.
Literally, I was like, they changed the rules of addition.
I told you earlier, it's not necessarily you that's wrong here, right? And I haven't even started the 3 classes per day the teaching schedule yet, so. Okay. So part B is just simply going to add in the OH minus and the H plus to that. Well, really, we're going to subtract the H plus. But at pH 10.5, the H plus is going to be really, really small, and it's a small impact anyway because the equivalent weight is 1. So we can kind of do the same process. Equivalent weight for H plus, like I said, that's 1 divided by 1. Equivalent weight for OH minus is going to be the same thing as a molecular weight for OH minus, which is going to be simply oxygen is 16 plus 1 for the hydrogen is 17. So equivalent weight 17 divided by 1. So we can say that's milligrams per milliequivalent. And then when we convert from our concentrations, which we know that the H plus is 10 to the minus 10.5, OH minus is going to be 10 to the minus, and what we can do if we want to is say 14 minus 10.5, so that's 10 to the 3.5. We can get those numbers in moles per liter and then convert that into milligrams per liter and then convert to milligrams per liter as CaCO3. So it's actually slightly more involved because we have to go from moles per liter, but anyway, it's 3.16 times 10 to the minus 11th for the H plus, and 3.16 times 10 to the minus 4th for OH minus. These will correspond to, if we convert them, I don't have it written here in front of me, but if we end up converting them to that as OH minus and, or excuse me, as CaCO3, then we get values of 1.58 times 10 to the minus 6 milligrams per liter as CaCO3. So a very small number, and OH minus is 15.81. And actually you can see these numbers are parallel through the whole thing because it was 10 to the minus something 0.5, and it turns out that just works out. So that's just 15 milligrams per liter as CaCO3. Okay, and this time if you add the 15.81 to the 85.08, that's where we're getting a number that's about 100.9. Finally, it actually becomes possible. If you notice, we also would need to subtract the 1.58 times 10 to the minus 6, and that's just going to be way out there and as a rounding error, right? So pretty much ignoring that. So 100.9 milligrams per liter as CaCO3. All right, any questions or issues? All right, so the last problem, we have some water quality constituents written out for us. A facility plans to soften this water prior to industrial use, and we have to answer the following questions for this water. Part A is, what is the concentration of magnesium carbonate hardness expressed as milliequivalents per liter in the water? So the milliequivalents, this is actually slightly simpler than the as CaCO3. We just have to do the conversion from using the equivalent weight, right? So instead of taking milligrams per liter, we can take the molar concentration of X, multiply that by the equivalent weight of X, and that should be it, right? Because that's moles per liter times milligrams per milliequivalent. Of course, we have moles here. We actually need millimoles, so we would need 1 millimole per 1 mole, 1,000 mole, excuse me, 1,000 millimoles per mole, right? Yeah. So then that should give us the conversion route. Okay, so then that'll give us a way to write our system in terms of milliequivalents. I think we could also just convert straight from milligrams per liter actually into milliequivalents. At any rate, what I wanted to show you is if we consider the plot or the 5 equations in the book, is first remove the CO2, and then it was remove essentially the calcium carbonate hardness, and then remove calcium non-carbonate hardness if you have it. Then we get to the magnesium carbonate hardness, magnesium, and I guess it was 6 steps, right? Or maybe that was it. Magnesium non-carbonate hardness. Okay, and each of these corresponded to adding lime or potentially lime and soda ash in order to precipitate calcium carbonate and potentially magnesium carbonate. So that system, you could take a look at the plot, the bar charts in the example problems, and really see if you had this much calcium and then you had this much bicarbonate, let's say, then essentially you have this much carbonate hardness, calcium carbonate hardness, Ca carbonate hardness. And then you'd have no non-carbonate hardness because you have no calcium that goes beyond that. And then maybe you have this much magnesium starting from that point. Then you have this much of it is magnesium carbonate hardness. And then this much would be magnesium non-carbonate hardness. So essentially, you can break apart the system into the different components of what you need to remove. So this problem really was all about setting up an kind of a calculations to determine how much you had. And if you follow the example, the table in the back of the example that we worked through in class, you should be able to set up what these components are essentially equal to in milliequivalents per liter. So essentially just solve all these for milliequivalents per liter, and then you can get these answers, which I'll come back to. But this is what it looked like for me. I went ahead and wrote out each component, the molecular weight, the equivalent weights, and then converted that to milliequivalents. And then I went on to a second table where I was doing these components of those reactions, because these were those 5 reactions, right? To remove the CO2, calcium carbonate hardness. I think I misordered this, I'm sorry. It's calcium carbonate hardness, magnesium carbonate hardness, then calcium non-carbonate, and magnesium non-carbonate. I flipped 2 of those and I apologize. It makes sense, you have to get rid of all the carbonate before you can go on. Well, it turned out that we had enough calcium to remove some of the carbonate, but not all of it. And so then we had consumed all the calcium, then we went on to magnesium. Then that means there's no calcium left for non-carbonate calcium. So this was all 0. And then we get the magnesium non-carbonate hardness. So essentially what you do is you take this value here, you're pulling it straight from here. So this goes there. Then after that, you've got, and I'll just put a 1 next to each of these to kind of denote that. For the calcium carbonate hardness, well, it was essentially how much calcium did we have. So 2 goes with this. So that's the milliequivalents there. That's the answer to that component. I think that's the answer to the question, right? Okay, the first question is concentration of magnesium carbonate hardness. So then once we get to that, and this is going to be our answer to part A, essentially this value is coming from our third reaction listed in the book, and we take the remaining bicarbonate and we have to divide it by 2 because we're actually consuming 2 bicarbonate for every 1 magnesium we remove. So that's where that comes from, and that's where the other answers come from. Happy to go into more detail on that for you. I'm going to go ahead and jot down these answers. You're free to go. Any last questions before you do? I'm not going to make you do this Excel and this involved of a problem for the exam. All right, so we'll see you on Thursday.
Yeah.